We're finishing up Chapter 16 today by talking about continuous random variables. So a random variable that can take on any value within a range is called a continuous random variable. It's continuous because it can be any value from 1 to 10, or whatever your range happens to be. Any single value won't have a probability, but continuous random variables have means. By means, we mean expected values, and variances, and by variance, we mean that we can also calculate the standard deviation. We won't worry about how to calculate these means and variances in this class, but we can still work with models for continuous random variables given parameters. So we're not necessarily calculating the means or the variances, that is more advanced statistics, but we can still use them based off of the models that we currently know. The good news is that nearly everything we've said about how discrete random variables behave is still true of continuous random variables as well. So we add them together in the same way, we multiply them by a constant in the same way, all of that still applies. When two independent continuous random variables have normal models, so does their sum or difference. So it's important that the random variables be independent. What this allows us to do is it allows us to use the normal model to be able to calculate normal probabilities when we're dealing with questions about the sum or difference of independent random variables. Let's look at an example of continuous random variables. A used car dealer runs cars through a two-stage process to get them ready to sell. The mechanical checkup costs $50 per hour and takes an average of 90 minutes, with a standard deviation of 15 minutes. The appearance prep costs $6 per hour and takes an average of 60 minutes, with a standard deviation of 5 minutes. We're going to use this scenario to answer a couple of different questions. The first one is that we want to know what are the mean and standard deviation of the total time spent in preparing the car. What I would do here is I would kind of write out a basic equation. So we want the total time spent in preparing the car. So to prepare the car, we have the mechanical time plus the appearance time. So my expected value, so my expected total then, would be the expected value for the mechanical time plus the expected value for the appearance time, which would be the 90 minutes plus 60 minutes, for a total of 150 minutes. To find the standard deviation, remember, in order to find standard deviation, we have to convert the standard deviation back to the variance first, calculate the variance, and then find the standard deviation. This would be done by finding the variance of the total time, which would be the standard deviation of the mechanical time squared, plus the standard deviation of the appearance time squared, which would give us a value of 250. Then to find the standard deviation of the total time, we take the square root of our variance, so the square root of 250. So that becomes 15.8 minutes. Therefore, the expected time will be 150 minutes to prepare the car, with a standard deviation of 15.8. Our next question is to find the mean and standard deviation of the total expense. So now we're talking about the money. Now they gave us money as a rate of dollars per hour. So the first thing we have to do is we have to convert our expected values and standard deviations from minutes to hours. So the expected mechanical time was 90 minutes, which is 1.5 hours. And that had a standard deviation of the mechanical time of 15 minutes, or a quarter of an hour. The expected appearance time, they told us, was an hour, or 60 minutes, and the standard deviation for the appearance was 5 minutes, which is a tenth of an hour. So what we want to do here, again, is to come up with a basic equation that allows us to find the total expense. So our total expense, now the mechanical time, they said that it would cost $50 an hour. So we have to multiply $50 an hour by the number of hours, plus the appearance time they said would cost $6 times the appearance time. To find our total cost, we have our expected total would be 50 times the mechanical time of 1.5 plus 6 times the appearance time of 1.0 which gives us a total of $81. In order to calculate the variance of the total time, this would be the variance of 50 times the mechanical time plus 6 times the appearance time. Since I'm multiplying each variable by a constant, remember when we calculate the variance, we have to multiply by the square of that constant. So this would be 50 squared times the variance of the mechanical time plus 6 squared times the variance of the appearance time. So this becomes 50 squared times 0.25 squared, because remember we have to take our standard deviation and square it to find the variance, plus 6 squared times 0.1 squared, which gives us a variance of 156.50. That gives us our variance, and then to find our standard deviation is the square root of 156.50, which is $12.51. So we ended up with an expected total expense of $81 with a standard deviation of $12.51. Our next question asks us what the mean and standard deviation of the difference in the costs of the two phases are. So this is very similar, but now we're subtracting instead of adding. So in this case, our expected difference is going to be 50 times the mechanical minus 6 times the appearance. So to find the expected difference, very simple, we just plug it in and go. So again, we're dealing with the costs, so again we're dealing with the hours instead of the minutes. So we would have 50 times 1.5 minus 6 times 1, which gives us an expected difference of $69. So we would expect that we're going to spend $69 more on the mechanical than we would on the appearance. In order to find the standard deviation, again we have to go through the variance first. So I would have the variance of the difference is going to be 50 squared times the variance of mechanical plus 6 squared times the variance of the appearance. Again, we're going to have to use the standard deviation and square it to find our variance. So it would be 50 squared times 0.25 squared plus 6 squared times 0.1 squared, which gives us the same variance as before of 156.50. Now, even though our original thought was to subtract, we actually have to add our variances, because even when you are subtracting, we increase our variation. So then to find the standard deviation of the difference ends up being the square root of 156.5, which again gives us a standard deviation of $12.51. So again, just to reiterate here, we have to add our variance because, again, even when we're subtracting, variation will still increase. So we always have to add. Our last example in this case is we want to know what is the probability that it will take longer to do the appearance prep than the mechanical checkup. So in this particular situation, we have to go under the assumption that we are following the normal model, which means that we have to go under the assumption that the mechanical time and the appearance time are independent. So remember that the normal model is a bell-shaped curve where your mean is in the center and you have 68% within one standard deviation, 95% within two, and 99.7% within 3 standard deviations of the mean. Now, we really won't be using the 68, 95, 99.7 rule that often. We also use a lovely equation of z equals your observed value minus the mean divided by the standard deviation in order to calculate our z-score, which is used to find the probability. In order to calculate the z-score, we need to find the mean and standard deviation of the difference between the mechanical and appearance time. So since we're not dealing with money, we're going to go ahead and continue using the minutes that they originally gave us. The expected difference is going to be your mechanical minus your appearance, which is going to be 90 minus 60, which is 30. Now remember that expected value is the same thing as your mean. So this 30 is equal to our mean. So when we have to use z equals x minus mu over sigma, the 30 is our mu, our mean. To find the standard deviation, so the standard deviation of the difference ends up equaling the square root, because we have to go back to our variance and then end up taking the square root of our mechanical time. So the standard deviation of the mechanical time was 15 minutes, and that has to be squared to get to the variance. Remember, even though we're subtracting, we always add when calculating variance and standard deviation, because variation always is increasing, not decreasing. Appearance time had a standard deviation of 5 minutes, and again I square that to get to the variance. Then when I add them together, and I get the square root of 250, which is 15.8. So we calculated that the mean was 30, and the standard deviation was 15.8. So using the normal model, which again is a bell-shaped curve, the mean is 30. Now we're trying to find the probability that it will take longer to do the appearance prep. So remember that our difference was mechanical minus appearance. If our appearance is going to take longer, we're going to end up with a negative number. So 0 is going to be our cutoff, and 0 minutes would be right there. And for the appearance to take longer, I'm looking for below 0 because it has to be a negative number then. So 0 ends up being our x value, or our observed value. So to calculate the z-score, we end up with z equals 0 minus our mean, which was 30, divided by 15.8, which is our standard deviation, and we get a negative 1.899. Then we use our z-score and calculate the probability that it is below that. So our lower cutoff would be negative 99, and our upper cutoff would be our z-score of negative 1.899. So this means that the probability that the appearance time is greater than the mechanical time ends up equaling 0.0288 or 2.88%. That is it for all of Chapter 16, and I will see you guys in class. Have a good night.